All right, AP students, welcome to your Unit 2 problem walkthrough regarding Lewis structures, molecular geometry, hybridization, and then sigma bonds and pi bonds. And so what we have going on is, let me make this, is that we have kind of a new way of looking at the 3D structure of atoms. We've introduced the Lewis structures, which is a 2D distribution, electron distribution illustration, which gives us a really great basis for understanding the 3D structure of how molecules are formed. Sorry, did I say atoms earlier? I definitely meant molecules. And what we have now is now we're trying to investigate through molecular geometry and hybridization the interplay between quantum mechanical model with the idea of 3D orbitals, zones of electron existence, with the 3D structure that we form when bonds are made. So one of the things I introduced was this idea of sigma and pi bonds, another way to characterize and confirm, honestly, the quantum mechanical model. And so what we have here is a sigma bond is present in every single molecule. And a sigma bond is same plane overlap. It's same plane overlap, usually between an S and an S or a P and a P, okay? And then pi bonds are same plane but parallel. They're a parallel overlap. So there's two portions to that orbital that overlap, all right? So again, this is kind of slightly separate to it's kind of I would just say remember that it's kind of its own way of categorizing bonds. So when we look at the structure of nitrogen triiodide, right? Nitrogen triiodide, we get the following Lewis structure. Okay, 1, 2, 6. Okay, with a 1, 2, a lone pair on the center atom. All right. So we know that for every single bond present, there is a sigma. Okay. So we have 3 single bonds, and therefore we have 3 sigma bonds. Now, double and triple bonds have 1 or 2 pi bonds. So if we had a double bond, we'd add a pi bond. If we had a triple bond, we'd add 2 pi bonds. All right. But since we don't have any of that, we just leave it here. Okay. At 3 sigma bonds that are formed in order to actually 3D structure wise with the quantum mechanical orbitals create 3 single bonds around nitrogen. So if we go down to the table, okay, we look at, I'm only going to do one of them and then you can do the rest. We see kind of a nice summary table of how we go from Lewis structure to 3D to valence bond theory and hybridization, the kind of evolution of understanding a molecule. So BF3, if you graph out its Lewis structure, will look like this. Now remember, B is unique because it's one of those less than an octet, incomplete octet, and okay with it elements. Okay, B likes 4 or 6. It's totally fine. And so what we get here is we get this Lewis structure. We would call this Lewis structure shape a trigonal planar. And remember, you do need to memorize the molecular geometries, all the molecular geometries. You need to memorize all of them, okay, all the way down to trigonal bipyramidal and the lone pair adjustments as well. Okay, and we know this is a trigonal planar because it has 3 electron domains from the 3 single bonds and no lone pairs on the center. So we know that this is trigonal planar because of that. Is the molecule polar? Well, we look at B and F, and we have only B-F bonds. Okay, so we know that they're pulling at an equal distance away from, or an equal angle around boron. We also have no lone pairs. So we have no lone pairs around the central atom. So there isn't any gigantic negative zone. And so we would say this is a nonpolar overall molecule. Now, I could have also calculated out the Pauling scale, all right, using the Pauling scale to determine if the individual bond is polar or nonpolar, and then looked at the symmetry. But oftentimes it actually is, I'm realizing it's actually more helpful to sometimes look at the symmetry first based off of the geometric shape and then look at the individual bonds. All right. And what is the hybridization? So now we're going from just the 3D structure based on Vesper theory, valence shell electron pair repulsion theory, right? That electrons want to get as far away as possible, or electron domains want to get as far away as possible. But now we're getting into, okay, how is this actually formed via the quantum mechanical understanding of the orbitals? And we say that hybridization-wise, a trigonal planar has an sp2 hybridization. 1s plus 2p's creates, okay, 3 sp2s technically, but we just call it, we characterize it one at a time. So we just say an sp2, but there technically would be 3 sp2 overlaps, one for each single bond formed. All right. And remember, for hybridization, you only have to memorize up to sp3 tetrahedral. You do not have to memorize the hybridizations involving the d orbital, but you do have to memorize all of the molecular geometry. Okay, so keep that in mind. And let's go ahead, and those are our two conceptual. Let's move on to our AP. So we're going to finish out problem 1, and then we're going to continue on in start problem 3 for you, but we will not finish problem 3. So problem 1, let's go to E. We've already started filling it out pretty successfully. We have a long FRQ. Remember, that's 23 minutes allotted on the AP exam, and it's worth about 10 points. And by about, I mean it is, sorry, it is worth 10 points. And what we have, we've been talking about periodic behavior, periodic similar property trends and chemical behavior. We've been looking at the potential energy graph for bonding, and of course the Lewis structure. And now we're asked to answer the following questions based on the diagram you drew above. So something about the AP, by the way, is if you get a previous question wrong, like let's say you get D wrong, you drew the wrong Lewis structure, but then you answer all of E, which is based on D, correctly, based on your previous answer. Like even if your previous answer was wrong, but your logic following it is right, the AP will still give you the points. It will mark you wrong for the initial error in D, but if you follow through with it correctly, it will still mark you right for E. Okay, so okay, so let's go ahead and try this out now. Answer the following questions based on the diagram you drew above. What is the hybridization of the carbon atoms in C2Cl4? So according to my structure, both carbon, let's just label the left carbon as carbon 1, right? The left carbon and carbon 2 as the right carbon. Both of them have a similar bonding structure, right? We have both have a double bond for one electron domain and then 2 singles coming off of it. All right. So hybridization wise, what we have is when we kind of look at one central carbon at a time, we see each carbon have 3 electron domains. Okay, 3 electron domains, giving us, and no lone pairs on it, giving us a trigonal, okay, planar, which is an sp2 hybridization. All right. So that's that one. And then we move on to the next question. And we say to ourselves, okay, what is the approximate chlorine-carbon-chlorine bond angle? So you, just like with the molecular geometries, will have to memorize the relative bond angles. And remember, bond angles are based off of Vesper theory. So the reason why we can determine the molecular geometry is because of the valence shell electron pair repulsion theory that tells us the bond angles formed to maximize distance between the repulsive forces, and therefore giving us the 3D shapes that we call linear, trigonal, planar, and so forth. We say to ourselves, well, trigonal planar with no lone pairs, right, on the center atom will give us an sp2 hybridization. with a 120-degree bond angle. Okay, 120-degree bond angle. And then is the C2Cl4 molecule polar? The answer, if we look at the geometry of it, it is pretty symmetrical, right? You could theoretically just draw a line down the center of the molecule, which is actually the center of the double bond between the two carbons. And you would see we have mirror images of one another. That would mean it's like an equal pull. If you think about a tug of war pull of pulling the electrons, you have equal pulling, which would cancel out. That rope wouldn't go anywhere. So we would say that because of the symmetry or the equal pull of the polarities, because carbon and chlorine are definitely a polar individual bonds, but the overall molecule will have the canceling out of those individual polar bonds. And what we get is a non-polar molecule due to the symmetry, okay, of the molecule shape itself. All right. And of course, you have equivalent terminal atoms. Okay, so you have the same level of polarity at the individual bond level, and then you have symmetrical shape, all going to cancel out. Okay, so moving on to question 3. Here we're just going to start this one up. All right, question 3. So what we have here is, and oh, did I forget to erase my stars? Nope, I erased them. What we have here is we have a chart of nonmetals and the compound formula, and we say some binary. Binary means, right? Binary means two element binary. Compounds that form between fluorine and various nonmetals are listed in the table above. A student examines the data table and poses the following hypothesis that the number of F atoms will bond to a nonmetal is always equal to 8 minus the number of valence electrons in the nonmetal atom. Okay, so we're getting a theory. And this is a short FRQ, so this should take about 9 minutes, worth about 4 points. And based on the student's hypothesis, what should the formula of the compound that forms between chlorine and fluorine? So the number of F atoms that will bond to a nonmetal is always equal to, okay, 8 minus the number of valence electrons in the nonmetal. So the nonmetal here is chlorine. So it would be, that's like bonding to fluorine. So it would be 8 minus 7, which would give us 1. Okay, so the compound should be chlorine F, ClF. Okay, and just to make it super clear, ClF should be the compound, and therefore the formula is ClF. That is not an I for iodine. That is not an I. That is Cl for chlorine and F for fluorine. All right. And then in an attempt to verify whether this hypothesis about fluorine compounds is true with other halogens and find the formula Cl, chlorine, ClF. In the box below, draw a complete Lewis electron dot diagram for the molecule for ClF3. So here you would use your rules, okay? Your Lewis structure rules determine the total amount of valence electrons available to us. So TVE is going to be equal to each chlorine brings 7, okay? And each fluorine brings 7 as well. So you get a total of 28. So your structure, your chlorine is written first. And it also, we kind of know that it has to be the center one just simply because we have 3 Fs around, okay? And we tend to write the central atom right first. And we know that chlorine is slightly less electronegative than fluorine, so it would also serve as the relative central. So we get ClF 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Okay, we've used up 18 plus 6 for the initial, right? Structure and distribution. So 18 plus 6 is minus 24. We'd have 4 left. Well, we can't put any more on the terminal, so we go to the center atom. And we have an interesting scenario here. Here we have chlorine taking on 2 more lone pairs. And here we have an expanded octet with chlorine, which theoretically is possible because chlorine is an element in row 3 or above, So I don't know why I raised my own hand on the Zoom. Row 3 or above. So it could technically have access to a 3D orbital. It's not very common at all, but this would be according to the student's hypothesis, the structure that would have to form for CLF3. Okay. And what we get is two possible geometric shapes for CL. I just made the mistake. CLF3 molecules are trigonal-planar and T-shaped. The student does some research and learns that the molecule has a dipole moment. Okay, a dipole moment tells me that the entire molecule is polar. We have a sum polarity between all the interactions of the relative electron domains. We have a sum polarity. We have a sum vector. For those of you that are into physics, right? What's your sum vector? Okay. Which of the two shapes is consistent with the fact that CLF3 molecule has a dipole moment? Justify your answers in terms of bond polarity and molecular structure. So immediately, you should rely right now on your memorization of the molecular geometry shapes. And we know that trigonal planar is only possible with 3 electron domains and no lone pairs, LP. But T-shaped is accomplished, okay, through I believe, 5 electron domain, but 2 are lone pairs, which, by the way, fits exactly the model that we have drawn above. So what would we say is the T-shaped geometry, all right, is consistent because, okay, it requires asymmetry, right, due to lone pairs around the central, and unequal dipoles, or because it requires asymmetry or unequal dipoles that do not cancel out. Right? And here again, it's due to the lone pairs. Okay. So that's kind of the overview for those 2 AP questions. Remember, just as we begin to approach the Unit 2 quiz, your Unit 2 AP problem workbook completion can be shown to me at any point in preparation for the Unit 2-3 test, combo test that will be taken a week or so, a couple weeks from now, okay? Depending on what semester you are falling in. So here we have the end of our Unit 2 material. Good luck, you guys, studying for the quiz tomorrow. There's a lot of memorization in this unit, so I'd get Quizlet out. I'd just go through it with a friend over Zoom or Discord or whatever new modern version of chatting with friends online is. So good luck, everybody.